What's going on YouTube? This is Ipsec, and we are going to be doing Safe from HackTheBox, which was labeled as an easy box. I think this one's medium because the initial foothold to get on the box is exploiting a program via a ROP chain. It is a basic ROP chain, but nonetheless, it is binary exploitation, a topic that many people struggle with. Once you get on the box, there is a keepass file along with a few images. You have to use either John to keepass or keepass to John, along with the keepass file and image to create hashes for it, and then you can either use John to crack it or hashcat. If you use hashcat, there is a bug, I believe, where you can only crack one hash at a time, so you just got to run hashcat multiple times. So let's just get into the box and we can see what's going on. As always, we start off with the nmap, so -sc for default scripts, SV enumerate versions, OA output all formats, put in the nmap directory and call it safe, and then the IP address, which is 10.10.10.147. Can take some time to run, so I've already ran it. Looking at the results, we have just two ports open, the first one being SSH on port 22, and its banner is telling us that it's a Debian box. We also have HTTP on port 80, and its banner is telling us it's Debian as well, and that it's an Apache HTTPD server. We do have a few nmap scripts that ran, the important one being the HTTP-title, and that's just showing us that it's the default Apache web page. So we can validate this by just going to 10.10.10.147, and we see, yes, this is the Apache It Works page. I'm just going to quickly go to like robots.txt to see if I see anything there. Nothing. So let's go throw this over into dirbuster. So gobuster -u for URL. Actually, before that, specify dir mode, u for URL, and then the word list with -w, user share word list, dirbuster directory list 2.3 medium, and then -o for out file. We'll just call this root-directory. And then let that run. While this goes, there's really not much to do, so I'm going to also do a full port scan with nmap with nmap-p-. I'm also going to specify the -v flag for verbose, and that's just going to show us open ports as it does find them, and then the IP, which is 10.10.10.147. While that goes, I guess we can go and look at this page. If you do a Control-U to view the source, you can see there is indeed something hidden about this page. There's a comment that says MyApp can be downloaded to analyze from here. It is running on port 1337. So if we let nmap go, it'll eventually find port 1337, but we can just hit this on our own. So 10.10.10.147, port leet, and we just get, what do you want me to echo back? And it says get/http/1.1. So this is kind of an indicator that we probably should use netcat or telnet, because when we make an HTTP request, this is the very first thing our browser sends. So if we open up a new pane and see 10.10.10.147 port leet, and let's do ncat. Maybe that'll be better. Oh, ncat's not installed. apt install ncat. I thought that was always installed. Let's see. It's just weird how NC was handling this line break. If we do 10.10.10.147, 1337, we're just getting that. We put some stuff here, and then it outputs this text. I'm just curious if ncat is going to handle this any differently and print this text, letting us type here. ncat 10.10.10.147, 1337. Nope, same behavior. So I wonder if that's just a way the program's coded. But we put some text here. It's going to say, what do you want me to echo back? And then output the text. And we can't do it multiple times. So what I'm going to do is, let's say, echo back $, who am I, looking for command injection. Echoes that back fine. Let's do backtick. Who am I, backtick? Does that fine. So at this point, let's go download the app. And it says the app can be downloaded to analyze from here. So if we just do MyApp to download this, and then save the file, we can go over in terminal and move it out of the download. So move downloads MyApp. put a period for current working directory, and then let's open up Ghidra to analyze this app. We could also just execute it and see what happens, but I always like opening up in some type of reverse engineering tool first. So new project, non-shared, root HTTP safe, make dir Ghidra, and project name, this will be MyApp, finish, open this, and let's fix the size a little bit. There we go. Import the file, MyApp. Okay. Analyze it, select all, analyze. Probably don't need a select all, but I'm just lazy and it's a small app, so I'd rather do everything than nothing. So let's go over into the functions, and then we can go into main to see what this does. Looking at this decompiled thing, I wonder if I can make this bigger. Properties, display, see style, font. Here we go, 16. There we go. So that's probably easier to read. So we can see the main function. We have a variable right here. It's assigning 112 bytes. And then it's executing system. And then passing it user bin uptime as that call. So this is why when we do an NC on this port, it runs this. So on our box, if we run uptime, we get the same exact thing. So runs uptime via a system call, and then does a gets, and then a puts. So just analyzing this, I know that this is going to be vulnerable to a buffer overflow, but we can test it first because we're only assigning 112 bytes here, and gets and puts is just vulnerable functions. So if we put in more than 112 bytes, then we'll start overflowing the buffer and then get an overwrite. So if you wanted to test this on your own, the standard way to do it is just first make this executable and then run gdb MyApp. And I have Jeff installed. If you don't have that, go to, I think the last video I did, Ellingson, and I go over installing this. But if we just put a bunch of A's, actually, let's be scientific. We can do python-c print a times 112. And then we can put this in. And we see it exits normally. If we put a times 113, we'll do 114. It'll probably exit normally because we haven't overwrote enough to actually cause damage to the program. And we exit normally. Let's do a times 128. And then copy this, run. And now you can see what the seg fault looks like. So let's see exactly where we crash. In this program, we see we're on a return function, and return is going to go to RSP. So looking at the RSP register, we see just all A's. So in order to see where we actually return, we need to put some type of pattern on this buffer so we can see exactly where in the string. So I'm going to run pattern create 128. Let's just do 200. No real reason, but keep it even. So now when we run this, we can paste it. And then if I look at registers, we can see RSP is here. If you want to take shortcuts, you can just do pattern search, then $RSP. Handles this as variables just fine. And we can see at offset 120, it found it in little endian format. At offset 113, it found it in big endian. So little endian, it says, is likely, so let's test that one first. So what we're going to do is do A times 120 plus B times 8. And then we can do plus C times 8 as well. Don't have to do the C thing, but it's nice to see where stuff goes in afterwards sometimes. So that's why I do that. So now when we run this program again, we can see we still seg faulted, but if I run registers and we look at RSP, we can see the B's and then the C's. So if we put a memory address here, then we can continue through execution of the program. So I didn't mean to exit. We do like, let's put the memory address of main. So looking at main, that's going to be at 0040115F, 40115F. So let's do v exploit.py and 0x4115F. And this will be main. So I'm just putting that note there because we have to create the PwnTool skeletons. So from pwn import stir context terminal is equal to tmux new window. And then P for process is equal to gdb.debug MyApp B main. And then context OS equals Linux. Arc is equal to AMD 64. Okay, so now if we do junk is equal to A times 120, and then we put the main on the stack, so we'll do call main, I guess, maybe. P64 0x4115F. And then P dot, I'm gonna have to do like receive lines and print. Oh, we can just try P dot send line. Junk plus call underscore main. And this has to be encoded. If I don't, it's in string format, and call main is in byte format. So doing this dot encode turns this from a string into a byte, so we can now concat these two variables. So let's do Python 3, exploit.py, breakpoint 1 hit, because we're breaking main, so I can just do continue, and command aborted. R, C, R. So I'm guessing I have to do a receive line call until we get this. So let's copy this variable, go back into our code, the exploit, then have it do a receive until, and then that line. So now when we run exploit, if we do Python 3, exploit.py, we hit our first breakpoint, which is main, we do continue, and we get hit by another breakpoint on main. So we have verified that our buffer overflow is working. So what we want to do now is look at what we can do. So going into Ghidra, we want to hijack this system call. However, we don't have a way to put something on the stack. So if we look at this, where is it? Crap, did not mean to click that. We can break, where is it? What is that system call? Right here, 0x40116E. So if we go back into our script, 0x40116E, I think I said, this will be system. I don't know why I actually did that. Let's just execute this. And then break 0x40116E. That is correct. And then continue. We'll immediately hit a breakpoint, but this will be, or it should have been at the call. b star 0x 40116e 40116e. Continue. Breakpoint app stopped. Main +4. I don't think this is it. Oh. Yeah, it is. So right here is the system call. So what we're probably doing right here is loading the first variable into RDI, because this is load effective address. So in 64-bit land, variables are executed as registers, and the order is RDI, RSI, RDX, RCX, R8, then R9. So since system is only taking one argument, which is user bin uptime, only one argument is going to get loaded. So that's why we have it loading it in RDI right here. So if we do X, whoops, I'm still in tmux mode. No, there we go. X/S for string, RDI. We can't access anything. Let's go that. Can't access. So right here is what we're loading in. So after this, we should have a variable in RDI. And if we do registers, we can see RDI is just 0x1. So do one more step. And then we do X/X RDI. We can see we loaded the string, user bin uptime. And if we do registers, we can see that RDI is set to the memory address of where the string is. So all we have to do to exploit this now is try to find a way to put our string inside of RDI. And if you look through this app, we can look at all the other exported functions. So this is main. What's pink, I believe, is exported. What is blue is imported. And imported just means it's coming from libc. So blue means it's not within this binary itself. It's a linked function. There is a function called test, and we can't even decompile test. I don't even know what the source code of this would look like. But looking at the assembly, let's see. Can I change this easily? Registers. Come on, where's size? Colors. Properties. There's no properties there. So, I don't know how to change the size on this. My bad. Anyways, the first two things here are just setting up the stack for being in a function. We push the base pointer to the stack and then copy the RSP, the stack pointer, into the base pointer. This is just things to set it up. You can look down here as well into a different function, and you see those same two commands. So this code actually begins right here, where we're taking the stack pointer and putting it into RDI, and then jumping to whatever is in R13. So the stack pointer generally will contain the output of what things are called, because that's going to point to the very top of the stack. So when we go to main, let's go here. Wait, main. Okay. Right here, when we do this colon puts, the stack will, or not stack, the RSP value will most likely be whatever we put in here. So this gets this local 78. We can hit L here and then change this to be RSP. Or we'll put most likely RSP. It's generally not how you name a variable in this, but that's what we're doing. So this is going to be a pointer to what is going to be an RSP. And if we do a ROP chain to test to get into this function, like we had done to get into main, then we will push RSP into RDI and then do a jump to R13. So R13 we want to be system. So if we go back into terminal, we can do ropper -- search pop R13. Maybe put this in quotes. There we go. So we can see We have a call to popr13 here. It's going to do 2 other pops, so we'll just put null values in these 2 and then do a return. So we want to copy this address, and then here we can just exit. And then let's go back into exploit and add the memory value before we lose it on clipboard. And this is going to be popr13, pop. I don't care about the other pops, so that's why I just did that. Now we have to build the ROP chain. So the very first thing we have to do is put the string bin sh on the stack. So we'll do a variable called bin underscore sh is equal to /bin/sh \x00, a null byte, which is going to terminate the string and then convert this into byte format. This is going to be 8 characters, 1, 2, 3, 4, 5, 6, 7, and then this is all 1. So we want to adjust our junk to be 112. 120 minus 8 is equal to 112. So now that that's going to be there, we also have to call, we'll have to call system. So this will be libc, no, this will be, yeah, system. PLT system probably. Procedural link table. If we go to Ghidra, we can go to main, where it's calling system. Most likely right here. System 01 40116E. So 0x 40116E. Is that it? That doesn't look right. Let's see. We can exit this. Let's just do object dump -D MyApp grep-I system. Okay, so this is the one we want. 401040. I guess we can try 40116E. Let's see if that works. That's just going to be system. It'll probably work. Change to 410. Okay, and this should be P64. That stands for PAC 64-bit. So we'll also need to do the pop RDI function to get something into system. So pop RDI is equal to P64 0x41206. And then we need null P64 0x0. And the final piece is the memory address of test, so we can jump to it, which we'll call system. So if we grab this address, that is going to be at 401152. So put that there, and now we can begin assembling our ROP chain. I'm just going to get rid of that call main because we don't need it, actually. I was just demonstrating things. So junk plus bin sh. This is going to have the string bin sh on registered as the RSP variable. And now we're at 120 characters. So this is the first memory address overwrite into RSP. So we're going to put this as pop. It's not right to be RDI. This is actually pop R13, I think. 401206. 401-206. Yeah. So this is the pop R13 address. So later used as jump R13, treat as RSP. I don't know a good way to explain that off the top of my head, but There's that. And this we can say this is RSP into RDI, then jump R13. So RSP to RDI, jump R13. Okay. So we want to pop R13, and that's going to take the top value, which is going to be the memory address of system. And it also does two other pops. So we want to do null, null. And then we want it to return to test. So I think that's right. So what this is going to do is it's going to put binsh into RSP. Then it's going to put the system variable or system memory location into R13. And then it's going to get through the other two pops in that chain. And then return to test. And test will now execute it, hopefully. So if we did everything correct, this will work, which we probably didn't. So this is break on main, continue, and break on main again. Receive until this p dot interactive. Run. Continue. It may not be going interactive because it's doing some weird forking. So let's just try it on the live system. So let's try p is equal to remote 10 10 10 147, and it was on port fleet. So let's run this. Opening connection. And we didn't get anything. Let's see. It's going over the network. Remove that. Okay. Remember that weird like netcat issue I was having before when we did like netcat 10 10 10 137 leet 147, and it's not giving me that string. I think that's what's happening there. So that's why I removed that one line. If we just execute the program, we get what do you want me to echo back right away. So that is why I had removed this receive until, because I was thinking maybe it just never got it, and it works. Awesome. So we do this, do host name, we're on safe. So the one thing I want to test out real quick is will either these system addresses work? I'm guessing they should. So instead of 40166E, which was down here, we'll do 401040. So 401040 for system. 401, run this again, and it still works. So again, all you have to do is get to system. So now that we're on the box, we can do cd $ to go to home. Can't. Echo who am I? My bad. Just run who am I. Go into cd home user. Actually, let's just go into home. See who's on this box, if there's anyone else. Just user, so go into user. And since I'm in a weird interactive mode, I'm trying to get into .ssh, so I can drop an SSH key to get in. When I'm in this weird shell inside of PwnTools, I don't know a good way to get a full TTY, so I'm now just dropping a SSH key. So SSH keygen -f for file, we'll call it safe, and then chmod 600 safe cat safe.pub, and we will just echo this into authorized _keys chmod 600 the safe file. This is the private key, so sh-i safe user at 10 10 10 147, and we get a proper shell. So I can exit this, and we can figure out what we want to do with this box. I see a bunch of JPEGs and a KDBX, which is, I believe, KeePass database. So let's just grab everything. I'm going to exit out of the shell, make dir files, cd files, and we'll do scp -i ../safe. This is going to be private key. User at 10.10.10.147. And we want to copy everything to a local directory. Now that the file copy is done, let's just take a look at what these images look like. So I do nautilus dot just so I get a file browser, and we can see images look pretty standard. We can check exif tool to see if there's any hidden information in these. And glancing through, this looks like all the standard metadata associated with an image. So nothing too interesting there. We can also bin walk the images, but I'll just do one because I don't think it'll resort into anything interesting. Nope, they're just standard JPEGs. There is that KeePass database, mypasswords.kdbx. So my thought was we have to crack this. So I'm going to do, what is it, KeePass to John, locate stir to John. Locate John to stir. No, here it is. KeePass to John. This is what the file is. So I want to run this on mypasswords.kdbx. And let's do potential. Oh, we'll do KeePass hashes. So that's one. And then KeePass also has a thing to do key files. So if we do KeePass to John, you can do -k to specify the key file. So what I'm actually going to do is go through all the JPEGs and put them as key files. So we'll do for I in ls.jpg, do echo I done. So all that's going to do is get all the file names. So KeePass to John -k $i to do the file name, and then mypasswords.kdbx. We do enter, and we get a list of files or a list of hashes. Now, the one thing I want to do is replace my passwords with the file name or the key name, because the hash is only this piece. But if we just did all this, it can be a bit of a pain if we don't track the username of the hash, and the username being the key file. So I'm going to do sed, then double quote s/my passwords with $i g double quote. And now we see my passwords has been replaced with the key file name. So we can just do $KeePass hashes. So now when we take a look at this file, we have a list of hashes. So let's scp KeePass hashes to the Kraken. And I'm just putting it in the hashcat/hashes directory. And the Kraken is just a machine I have dedicated to cracking. You can do it on your host computer. Just don't do it in a VM because VMs are slow. So we want to do /hashcat -- example hashes and do less KeePass. It's going to be some weird casing. Is it 13400? There we go. So I didn't find it when I did. Oh, I always do KeePass with a Y. That's why. But right here, we have mode 13400. It's going to be KeePass. And this is what it expects of the hash. If you do the user flag, you can put something before the hash and a colon to keep track of it. So super handy feature. /hashcat -m 13400 -O hashes / I don't even know what I called this. Probably keepass hashes. There we go. And then the word list, which will be opt word list rocku.text. And we need the -- user flag because we have stuff before the colon. So this is going to start the crack. There's one weird thing with keepass and hashcat right now. I don't know if it's a bug on my end or just a bug in general. It only will crack one at a time. I noticed this when I went through the whole list, and it only said recovered 0/1. This should be 0/5 or 6, how many other lines we have in the hashes. So it's only taking the very first line, which is going to be whatever ends in CE7A96. I think that's just keepass with no key file. So you'd have to run through this cracking multiple times because hashcat wasn't picking them all up. Whoops, wrong file. This is keepass. Okay, spelled it correctly. So I think I remember. So CE7A96 is this one. So it's only taking the very first one. So let's put this at the top because I think it was 0547. Just doing a little bit of cheating, but I would go through each of these, let hashcat run, and we'll see if this works. Oh, recovered 1. So we can see the password is what I think of this challenge. If you do -- user now, not -- user, -- show, you can see it's keeping track of the key file. So we'll copy what I think of it, go back here, and we can do apt install kpcli. This is going to be the keepass CLI, and this will let us go into the database. If I had keepass installed, which I don't think I do, no, I do not, we'd just be able to use the GUI. We'll let that install and then use it. Finally done in updating or installing kpcli, so we can do kpcli-h. So we can do kpcli-kdb. My is going to be in the files directory, kpcli-skdb. My password.kdbx -- key. This is image 0547. Does that not have image 0547? There we go. And then hit enter, master password, type it, and then do help. And we can see what commands we have. So this is just a literal like command line system. We do ls, we can go into my passwords. ls, there is the root, so we can cat show, and then the entry number, which is going to be 0 for root password. And then the password is in highlight, so we can probably do, let's see, so a show that has the entry. Let's try show -a. It's not really explaining what those do, but there we go. Nope, that's all. So what is the other one? Show -f. There we go. -f will unhide it. So what we can do is now SSH root at 10.10.10.147, put in the password, and it doesn't let us in. But SSH may be configured to only allow to not allow root login. SSH is often allowed that, so let's just SSH back in with a private key, user at 10.10.10.147, and we can try a SU, which is switch user, put in root's password, and we're here. So we can do wc-c root.text, and we see 33 characters, which is an MD5 summoner line break. So that is the box. Hope you guys enjoyed. Take care, and I'll see you all next week.